All right, this is Honors Algebra 2 Pre-Calculus. We're doing the unit circle today, which is a video section that is technically part of 4.2, but we do it before 4.2. So this is our intro to the unit circle. So recall that there was a time in your academic life when filling out the multiplications tables was key. Like, it's probably been years since you've had to fill one out, right? That's super weird because at one point it was super duper important. Well, that's because it wasn't really the table that was important, right? The table that you can see right here, right, is a visual way to represent a ton of useful mathematical info. Once you know the info, nobody really cares if you can fill out the table. So as long as you can do 6 times 7 and get 42, it's cool. Nobody really cares. So in this section, we're going to learn the unit circle, which is basically the same concept. It's a visual way to learn a lot of really useful information that you're going to need. That's why it gets its own day today in class. So we're going to start with a little bit of basic trig. We'll learn how to get the values on the unit circle, because if you know the logic behind concepts, it's much easier to pick up how they work, right? And then once you've effectively learned how we do this, we'll talk about strategies to memorize the information effectively. All right. So let's start here with what the unit circle looks like. This is the unit circle. So you can see, if we compare it again to those multiplication tables, that it's similar in the sense that it's large, it has a lot of numbers, and it's a lot to memorize on the surface, right? So essentially, this is a circle that is centered at the origin and is 1 unit in radius, right? So it goes over to 1, 0, it goes over to up to 0, 1. Whew, excuse me. And it goes left to -1, 0, and it goes down to 0, -1, right? And all of these values have a radius of 1. So let's talk a little trig first. So you've probably seen some basic trig in geometry class, although I know a handful of you have not had geometry before taking this class. But basic trig, we learned 6 trigonometric functions called SOHCAHTOA. So essentially a trig function, right? A trig function is a function that relates angles in a triangle to the sides. Okay, that's what it is. And right now we're talking right triangles. When we get to chapter 6, we'll talk about how you can use trig functions in non-right triangles as well. But for right now, we're talking right triangles. So let's look at this right triangle. So if I have some angle theta, there's a hypotenuse to the right triangle, right? The hypotenuse is always the side that is across from the right angle, because it's a right triangle, so it'll have a right angle. And then adjacent and opposite are relative terms. Because, for instance, this side right here is adjacent to angle theta, right? But if I put an angle alpha up here, this side is opposite angle alpha, right? Because it's the side not touching angle alpha. So whether a side is opposite or adjacent is going to depend on what angle you're looking at. So if I'm looking at this angle theta, the opposite side is the side not touching the angle, right? And the adjacent side is the side that does touch the angle. So the sine function, right? It's written S-I-N-E, and we say sine. The sine function, sine of theta, is the opposite side over the hypotenuse. So let's say in this problem that I made this a 3 and a 4 and a 5, right? That is a right triangle. 3 squared plus 4 squared is 5 squared. So in this triangle, the sine of theta would be the opposite, which is 3, over the hypotenuse, which is 5. The cosine of theta is the adjacent side, which in this problem would be 4, over the hypotenuse, which in this problem is 5, right? And the tangent of theta, right, tangent theta, is the adjacent side, is the opposite side, which is 3, over the adjacent side, which is 4, so 3 over 4. The other 3 trig functions, cosecant, secant, and cotangent, are just the reciprocal of those functions. So in this problem, cosecant would be the flipped version of sine. It would be a 5/3. Secant, which is the flipped version of cosine, would be a 5/4, and cotangent, which is the flipped version of tangent, would be a 4/3, right? So that would be my 6 trig functions. The word SOHCAHTOA, right, this abbreviation that we have, SOHCAHTOA, right, comes from sine is opposite over hypotenuse, so sine opposite over hypotenuse. Cosine is adjacent over hypotenuse, and then toa, tangent, is opposite over adjacent. So that's where SOHCAHTOA comes from. All right, so looking at this triangle that I have here, where we drew this angle in standard position, right? This is an angle in standard position. The initial side is on the positive x-axis, and the terminal side is right here, right, with a length of 1. We have some point in space called x, where x is this side of the triangle, comma y, where y is this side. Ooh, excuse me, and the hypotenuse is 1. So using what we just learned about SOHCAHTOA, we're gonna find the sine, cosine, tangent, cosecant, secant, and cotangent of this triangle. So the sine is going to be, so relative to where theta is, y is the opposite side, x is the adjacent side, and 1 is the hypotenuse. So the sine of theta is going to be opposite, y, over hypotenuse, which is 1, so the sine is just going to be y. The cosine of theta is going to be the adjacent side, which is x, over the hypotenuse of 1, which is just going to be a 1. The tangent is going to be the opposite over the adjacent, which is y over x, right? And then cosecant, secant, and cotangent are just the reciprocals. So 1 over y, 1 over x, and x over y. And we'll come back to that a little bit more later. So what I've done here is I've shown you the 30-degree triangle, right? So this is a 30-degree angle in the unit circle, right? And what we're going to do is we're going to use some special triangles that you've probably seen in geometry. And again, for the folks that don't know geometry, don't panic. We're going to go ahead and use some special triangles. This is a 30, 60, 90 triangle, so a 30, 60, 90 triangle that you learn about in geometry class, to figure out what these empty spots should be on the unit circle. So we can see that this would be the x-coordinate, right? This side's x and this side's y, right? So if I look at a 30, 60, 90 triangle, a 30, 60, 90 triangle has a ratio of 1, that's the side opposite the 30, to root 3, which is the side opposite the 60-degree angle, okay, and to 2, right? So 1 to root 3 to 2. So if I wanted to figure out what x and y values are, I could set up a basic proportion, and I could say that x is to 1 as root 3 is to 2. Oh, look, the x-coordinate of this triangle must be a root 3 over 2. So there's a root 3 over 2. I could do the same thing with the y, right? I could say y is to 1 as 1 is to 2 and realize that y is a 1/2. So when we talk about the unit circle, we'll go back in a little bit, but this point on the unit circle is a root 3 over 2 comma 1/2, and it basically comes from a 30, 60, 90 triangle. All right, the next triangle we're going to look at is this 45-degree angle triangle, right? So that makes this a 45, 45, 90 triangle, right? And the ratio of a 45, 45, 90 triangle is 1 to 1 to root 2, right? That's the ratio for a 45, 45, 90. So if this is the x-coordinate and this is the y-coordinate, right, x and y, and I want to find them, I can say that x is to 1, right? This x is to this 1, as 1 is to root 2. We don't usually leave a root on the bottom, so if I rationalize this by multiplying by root 2 over root 2, I'm going to get that x is a root 2 over 2. Now you could do the physical work to find the y value, or you could recognize that the ratio is the same, 1 to 1. So if once you know that x is a root 2 over 2, the y is also a root 2 over 2, because again, y over 1, right, y over 1 should be equal to 1 over root 2, and then you get the same answer. So again, I just found the second set of points in the unit circle to be a root 2 over 2 comma root 2 over 2, and we'll move forward and talk about y in a sec. So this is my third and final of the special triangles, and it's actually one we've already seen before. This is the 60-degree triangle. The reason that's one we've already seen before is a 30, 60, 90 triangle is still a 30, 60, 90 regardless of which way you stand it up. The ratio is 1 on the side opposite the 30 to root 3 to 2. Well, I know that I want to find this x comma y, right? So what I can do is I can set up a proportion and say that x is to 1 as 1 is to 2. So x is to 1 as 1 is to 2, meaning that x is a 1/2 here, right? And I can say that y is to 1, right? Y is to 1 as root 3 is to 2, and I can recognize that the y-coordinate is a root 3 over 2. So now if we put all of those pieces together, what ends up happening is I get that this is my 30-degree triangle, this is my 45-degree triangle, this is my 60-degree triangle. And if we go back, my 30-degree triangle had a root 3 over 2 comma 1/2. So if we come back here, we get root 3 over 2 and 1/2. You can use that line in the middle as the division symbol if you want. I found that the 45, 45, 90 triangle had both coordinates as a root 2 over 2. So root 2 over 2, root 2 over 2, right? And then I found that the 60-degree triangle had the same two coordinates as the 30-degree one, but in opposite order, which makes sense because this is the same triangle just standing up on end. So I got that this was a 1/2 and a root 3 over 2. So those were the same coordinates, but just flipped. Now, I can also see just from my knowledge of how circles work, right? This is a 1 unit radius, right? So at 0 degrees, I came 1 unit out and no units up, right? And similarly here, since this is a 1 unit radius, right? This is 1 unit up and no units left and right, and it is a 90-degree angle. So you can see that I can fill out these values in the circle, right? The blue values I got from the special triangles, and we'll talk about what these empty lines are in a minute. So now what we're going to do is we're going to go ahead and use symmetry to fill out the other values on the table. So it's going to seem a little bit tricky, but I think once you get the hang of it, it's not so bad. So we've established that this was a root 3 over 2 and a 1/2. So here's my argument. This other point across here has to have the same y-coordinate, right? But it should also have the same x-coordinates, the same distance from the from the y-axis, except in the negative direction. So that's going to be a negative root 3 over 2, but it's the same point. I'm going to argue, so that's these guys right here, right? They're the same point, just in a different quadrant. In quadrant 1, things are positive, positive. In quadrant 2, I have a negative x and a positive y. In quadrant 3, I have negative, negative. And in quadrant 4, I have a positive x and a negative y. So I'm going to argue I can actually do all 4 of these points. This is the same point, right? You can see that these points line up, and I'm terrible at drawing things, but you can see that these 4 points all line up. They're the same spot in different axes, or in different quadrants. So I get a negative root 3 over 2, a negative 1 over 2, a positive root 3 over 2, because the x is positive, and a negative 1/2. And again, it's a little bit hard to squeeze in here, but you'll get the gist. Okay, so I used that one point I found, right? This was the 30-degree triangle, right? 30-degree triangle. I can use the 45-degree triangle. So I'm going to go ahead and switch to a different color, right? If I use the 45-degree triangle, I know that this 45-degree triangle had everybody as a root 2 over 2. Well, the good news about that is it means that all of these other ones, the one straight across, is also going to be a root 2 over 2 and a root 2 over 2. The only difference is that the x is negative. The one all the way down here, right, that 45-degree angle down here is also going to be a root 2 over 2 and a root 2 over 2, but they're both going to be negative. And then the one over here is the same root 2 over 2, comma root 2 over 2, except the y-coordinate is negative because I'm in quadrant 4. So that was the 45-degree triangle, right? So 45-degree triangle. Let's switch to green. All right. So up here, I know that the 30, 60, 90 and the 60, 30, 90 are the same triangle, just flipped in opposite directions, right? So I know that this is going to be a 1/2 and a root 3 over 2 because it's the same as this point, just flipped, because this is the tall, skinny triangle instead of the short, long triangle, right? So same point, 1/2 root 3 over 2, but the x-coordinate's negative. Same point, 1/2 and root 3 over 2, but both of them are negative, and I'll just squeeze those negatives in, right? Same point, 1/2 and root 3 over 2, but only the y-coordinate is negative, right? So what I've done now is just using some basic geometry information and the idea of symmetry on this circle, I've been able to find all of those point values. Again, I can logic my way through the ones on the corners. And I know there aren't corners, but we're going to kind of consider these axes corners. From here, I have an x value of +1 and a y value of 0. Here I went up 1, but didn't move left or right. Here I went left 1 and didn't move up or down. And then down here, we'll scroll down because I lost that one a bit. We went, didn't go left or right, but we moved down 1, right? So you can fill out all of those points on the circle doing that, right? So when we talk about filling out the degrees, right, I'm going to argue that you should probably fill in the degrees that you know really easily first. This is 0 and 360, right? The right angle is 90, right? The full line is a $1.80. And since you're adding 90 each time, this is a 270, right? So you can figure those out pretty quickly. So there are a few different ways to add the angles into your circle, right? One easy way to do it is if you notice, see how there's this big skip here, like this slice of pie is twice as wide as the others? This is adding 30, and then these tiny slices add 15. So from 0, I add 30 for the big step, and then 15, which gets me to 45, which I'm not surprised about, and then another 15, because that's another tiny slice, and then a big slice would get me to 90. So add 30, 15, 15, 30. Big jump means add 30, 15, 15, and then 30 again, right? Big jump means add 30, 15, 15, and then add 30, and you can check that you land at 270, because that way you know you're adding right. Add 30, add 15 for the little slice, add 15 for the next little slice, and then add 30, and I land at 360, right? So I can fill in the degrees just by adding as I go around. Honestly, you get to the point where you've done the unit circle enough that it's pretty easy for you to spot if a number's there and shouldn't be. Like if I see that I ended up with a 215 somehow, I know I added wrong because I know it should be a 225. Okay, so the last thing we're going to talk about is converting the radian measure real quick. Now you can do this in a bunch of different ways. If you've spotted a pattern already, that's great. But I'm going to go ahead and convert them by timesing by a pi over 180 for all of these, right? So 0 is still just going to be 0 radians, right? But 30 times a pi over 180, well, the 30 and the 180 are going to cancel, and I'm going to get a pi over 6. 45 times a pi over 180 is going to be a pi over 4, because the 45 and the 180 will cancel. 60 times a pi over 180 is going to be a pi over 3. We already saw that a 90 over times a pi over 180 is a pi over 2, right? A 120 times a pi over 180 is a 2 pi over 3, because you can cancel a 60. If we fill this out the rest of the way, a 150 times a pi over 180 is going to be a 5 pi over 6. A 180 times a pi over 80 is just going to, or 180 rather, is just going to be a pi. 210 times a pi over 180 should be a 7 pi over 6, because I can cancel 30s from the top and bottom. 225 times a pi over 180 should be a 5 pi over 4. I feel like I skipped one somewhere. Oh, I think I skipped, did I skip a 135? I did, my bad. Buck 35. Buck 35 times a pi over 180 should be a 3 pi over 4. It wasn't on the table, my bad. 270, oh, sorry, I skipped 240. So 240 times pi over 180. And again, you don't have to do all this by hand. I'm going to walk you through why I'm able to memorize. Like, I know these answers. That's how I knew I skipped one. I know this is going to be a 4 pi over 3. I can actually go ahead and tell you that this is a 3 pi over 2, and it's a 5 pi over 3, and this is a 7 pi over 4, and this is an 11 pi over 6, and this is a 2 pi. So my point is that while I'm walking you through this just this once, I'm not suggesting that you do that on the regular. Like, that's not the goal. And we're going to walk through some ways to memorize this. 300 pi over 180 is going to cancel to a 5 pi over 3. 315 pi over 180 is going to cancel to a 7 pi over 4. And then 330 pi over 180 is going to cancel to an 11 pi over 6. And then 360 pi over 180 is obviously going to cancel to a 2 pi, right? Okay, so what we're going to do is we're going to flip back a page. They want me to flip back to the page to the quarter circle, and by they I mean me, because I'm the one who wrote this ages ago. So here's the page with the quarter circle, and we're going to fill this in. This was a 0, this was a pi over 6, this was a pi over 4, and this was a pi over 3, and pi over 2, okay? So those are my values. Now, if we go back to this main circle for a sec, right, if I fill these in, I'm going to show you something kind of cool. So when you flip back and forth, and I'm not going to flip back and forth, I'm going to be honest, I could flip back and forth, but I already know what the pattern is. So I'm going to go ahead and show you a little bit of the pattern as we walk through. So this was a pi over 6. This spot, also a blue point that I told you was the same basic point, this is a 5 pi over 6. I want you to notice they're both over 6s. This guy, also a blue point, that's a 7 pi over 6, also over 6. And this guy, also a blue point, that's 11 pi over 6. So essentially, what I want you to notice is that the pi over 6s all have the point root 3 over 2 and a plus or minus 1/2, right? They all have the same point, right? So all of them have that same value, the plus or minus root 3 over 2 in the x-coordinate and the 1/2 in the y-coordinate. Now if I go to the red, right, so we saw this was pi over 4. Well, this one, and you can just trust me, or you can flip back in your notes because we just did it, this is 3 pi over 4. This one's 5 pi over 4, and this one's 7 pi over 4. Notice that those are all the same point. They're all root 2 over 2, comma, root 2 over 2, and they're also all the pi over 4s. So all the pi over 4s are going to be a root 2 over 2 and a root 2 over 2. Sure, there's a plus or minus for both of them, right? Like depending on what quadrant you're in, but they're all root 2 over 2s. And then the last one that I did in green, this was a pi over 3, and it's not going to be an accident that all of these are going to be pi over 3s. So that's a 2 pi over 3. This is a 4 pi over 3. This is a 5 pi over 3. Right? And all the pi over 3s are going to be the exact same point as this, but flip-flopped, right? So flip-flop. So they're going to be in the opposite order, right? Instead of being the root 3 over 2 followed by the 1/2, it's going to be the reverse. The 1/2 will be first, but they're all the same point. And then in terms of the corners, which again, I realize they're not fully corners, it's honestly easiest just to memorize. They're the pi over 2's, right? So this is pi over 2. This is 2 pi over 2, which is just pi. This is 3 pi over 2. And this is 4 pi over 2, which is the same as 2 pi. So that crazy blob of stuff, that's your unit circle. So if we go back here for a sec, what I want you to spot about all of the pi over 6's is that they all have the point root 3 over 2 comma 1/2 plus or minus for the quadrants, right? I'm just going to write plus or minus for the quadrants, right? The pi over 4's were all root 2 over 2 and root 2 over 2, again, plus or minus for the quadrants. And then the pi over 3's were the reverse. They were the 1/2 and then the root 3 over 2. If you notice that, it makes it a lot easier to fill out the circle. So what we're going to do last thing real quick in this video is I'm going to walk you through how I memorize the unit circle. And you certainly don't have to, but this is how, so normally in a regular school year, right, if we're not in the middle of a pandemic, we're going to have a thing called the unit circle challenge. And this is how I fill out my unit circle. You don't have to, but this is how I memorize it. The very first thing I'm going to do if I'm filling out my unit circle is I'm going to start with the points, right, and I'm going to do all of these points that I'm highlighting in yellow. I'm going to fill all of them in first, because they're all the same value, right? Like they're all root 3 over 2 comma 1/2, right? I'm going to do them first. I'm not even going to worry about the positives and negatives, honestly, at first, because I know what's going to happen to positives and negatives later. So I'm just going to fill in the numbers. Then I'm going to fill in these numbers, right? I'm going to fill in the root 2 over 2's in all of these spots, right? Then I'm going to fill in these guys, right? The 1/2 first and then the root 3 over 2 in the second spot, right? So once I've done that, what I tend to do next, and you don't have to do this, but I tend to do the radians next. So I tend to do actually let me make this the narrow one. I tend to do my pi over 6's, and I'm going to tell you how you can logic your way to those numbers in a second. Okay, I do the pi over 6's. So let me walk you through how you can logic your way. You know that this slice, this yellow slice right here, is a single pi over 6, right? That's the measurement of this slice. Well, wouldn't pi be the same as 6 pi over 6? So wouldn't 1 shy of 6 pi over 6 be 5 pi over 6? And 1 more than 6 pi over 6 would be 7 pi over 6? So I can figure out that those numbers are 1 above or below the number 6, right? Because if I measured this in sixths, 6 pi over 6, I know that this should be one of these angles less than 6 pi over 6, which would be a 5 pi over 6, and this one should be 1 more. By the same argument, I'm going to argue that 2 pi is a 12 pi over 6. What's 1 shy of a 12 pi over 6? Well, that would be an 11 pi over 6. Then I'm going to fill out the pi over 4's, right? So I see I have a pi over 4 here. Sorry, I'll make that the thin angle, the thin line. So I see that this is a pi over 4, and I say, okay, cool. I get that this whole angle is a pi over 4. Well, I know that pi should be a 4 pi over 4. So what's 1 shy of 4 pi over 4? Well, that's a 3 pi over 4. What's 1 more than a 4 pi over 4? Oh, hey, that's a 5 pi over 4. And by the same token, this 2 pi is actually an 8 pi over 4. What's 1 shy of an 8 pi over 4? A 7 pi over 4, right? Right, so I'm going backwards a pi over 4, right? This is plus a pi over 4. This would have been minus a pi over 4, right? So I'm able to go backwards and forwards to figure out the values. I then do the same thing with the blue, right? Oh, and I could have highlighted all of your, all of these in green. So that's green, this one's green, right? So now I'm going to do the same thing with the pi over 3's, right? I know this guy is a pi over 3, this guy is a pi over 3, and this guy is a pi over 3. So I know this whole measurement is a pi over 3. I know that pi is the same as 3 pi over 3. So what's 1 less than 3 pi over 3? Well, that would be 2 pi over 3, right? What's 1 more than 3 pi over 3? Well, that would be 4 pi over 3. And I know that this guy is also secretly a 6 pi over 3. So what's 1 less than a 6 pi over 3? It's a 5 pi over 3. So that's how I can figure out all those numbers. So once I've done that, I think everything else in the circle is actually pretty straightforward, right? From there, I'm probably going to go ahead and fill out the corners, right? I'm going to say, hey, I've got this corner and this corner and this corner and this corner, right? And mostly that's just which direction you're moving, right? It's a 1, 0 or a 0, 1 in every direction, just depending on positive or negative, right? And I'll fill out the 0 and the 2 pi and the pi over 2 and the pi real quick. And then for the degrees, right, I'm probably just going to go around for the degrees, and I tend to just work around the circle in degrees. I start at 0, I add 30, 15, 15, 30, 30, 15, 15, 30, 30, 15, 15, 30, 30, 15, 15, 30, and I end up back at 360. And once I've done that, I've filled in the entire circle, right? I know the whole thing, I've got the entire circle. It really is all about symmetry. And one of the reasons I prefer to think in radians to degrees is you can see that if I see it's a pi over 6, my brain says, okay, the question asked a pi over 6. I have to figure out which pi over 6, like which quadrant is it in, but I know that these are the points already without actually spending a lot of time in it. Now there is one other way to get the radians that I thought I'd show you. I don't use this method, but it's definitely a way that I know some people have found helpful. Each one of you, oh my bad, each one of you is probably going to have your own different method for finding the number of radians. Like, that's fine. Another way to do this, if you don't like my idea, and you can also use this for the degrees, if you don't like the idea of having to memorize the different spots, is you can cut all the big angles in half, and then you can count in pi over 12s. So what you can do is you can say this is a pi over 12, which is not in the unit circle, but this is a 2 pi over 12. Well, look what 2 pi over 12 simplifies to. It's a pi over 6. 3 pi over 12, oh hey, there's a pi over 4. 4 pi over 12. And notice those ones that we inserted on the circle, they don't show up because they don't simplify. Like 5 pi over 12 doesn't simplify. But 6 pi over 12 would give you your pi over 2. 7 pi over 12 isn't on the circle, but 8 pi over 12 would definitely simplify to 2 pi over 3. 9 pi over 12 would give you your 3 pi over 4. 10 pi over 12, if you cancel to 2, would give you 5 pi over 6. 11 pi over 12 doesn't show up on the circle. 12 pi over 12 is definitely a pi, right? And that's how you know you're doing it right. And you can keep working your way the entire way around the circle. That's another way to find the, and you can also do that with the angles, right? This is 15 degrees because you cut it in half. 15, 30, 45, 60, this would be 75, but it's not on the circle. 90, this would be 105, but it's not on the circle. 120, 135, 150, this would be a $1.65, but it's not on the circle. Like, you can do that to figure out all of the angles, and both in degrees and radians, if that's something you like. All right, so in our next video, we'll actually do 4.2 properly, not just the unit circle, and we'll talk about how to use this a bit.